So is it working now? Can you hear us well? Okay, great. So where is the camera there? So you didn't hear my introduction of Pei here, but we're extremely welcome to have Pei here. And this is the first out of 8 lectures. And the format, so to speak, of the lectures is that Pei will speak for 80 minutes. Then we will have about 10 minutes break. And after that, there will be 30 minutes of questions. So if you have any brief questions during the lecture, please ask them, but let's keep the longer discussion questions for the part afterwards. I'm sure some of you also have questions on the formal PhD course and course projects and so on, and you can ask me or Patrick about that afterwards. But this at least is the first out of 8 lectures, and we are very happy that you are having this course here at Pei. So very welcome.
Thank you very much. Thank you, Robert, for the nice introduction. And thanks everyone for coming to this course or sequence of lectures. Well, today, the first one, you'll see the title, we're going to talk about artificial general intelligence, especially what they want to do and how to do it, the big picture part. So everyone know AI, right? But we have to start from there. So computer was invented initially for numerical calculation, but very soon many people realize they can do other mental work. Then naturally lead to the question that whether it can do all types of mental works, or whether we can really use it or build it into a thinking machine or electrical brain, no matter whatever you call it. That's the basic idea of AI. Right? Everyone knows that. But pretty soon, people realize this is much harder than expected at the very beginning. So gradually, this field actually changed its direction. Instead of talking about thinking machine, they tend to special purpose applications and tools, okay, which are very successful, but is not really what AI was at the very beginning, which is also true actually for the recent great success of machine learning. Even though they have achieved a lot of things, some people still think there lack some way to, if we are still talking about the original AI brain. Okay. So this naturally raises the question. Some people say this is not an issue. If we solve this problem, that problem, if we solve all of them, then we'll put it together, we have, a thinking machine. But there are also some other people who don't think that way. Okay. Intelligence to them maybe not cannot be really handled in this divide and conquer manner and solved one by one. So that's kind of like the idea behind what we now call artificial general intelligence. Okay. So in a sense, this is a new word, but for the old thing. Okay, this is still the old AI, or is more closer to the old AI. But the old AI has changed to something else. So a group of people say, no, we need to invent a new term to talk about what we want to do, which is clearly quite different, at least we believe, from what is currently called artificial intelligence. Okay. So in one sentence, I think you can say AGI is to treat AI as one problem, not as a collection or a group of problems which you can divide and conquer. Okay. And of course, there are also some people who don't, for this or that reason, they don't like or don't use this phrase. Some people say, talk about a human level AI or strong AI. Actually, it's more or less about the same thing. There are a whole bunch of other names. Okay, the label doesn't really matter. What matters is whether you see this artificial intelligence as one problem or a bunch of them you need to solve it one by one. So if we're talking about this this AGI research community, which Robert just mentioned, I actually started about 20 years ago by a small group of researchers who kind of like share the idea that we should treat AI as one problem. We should go back to the original dream of Alan Turing or the founders of the field. And we should still do that. And also, we believe the mainstream AI is not going in that direction. It's not just say how fast you have moved, okay? We think we need, for that problem, you need a different foundation, you need a different approach, okay? That's why, so in that year, in that period, a group of us start this new field. After some comparison, we settle down with the name artificial general intelligence by adding a G into it, even though at that time I'm not happy. I think this is redundant because to me, intelligence should be general by definition, right? So why bother? But yeah, there is a practical need to distinguish this from the other thing. So what we have, the visible part, you see that starting from 2008, we start an annual conference, which you see continued until this year, even though in the recent years have become a virtual and also a mixed conference. But we do have it every year, even though not very well known. It's still a small conference. And by the way, since I'm talking about this, there is quite a large possibility that the next year's conference will be here in Sweden. Okay, so I hope some people will be interested to get involved in that. We can talk about that later. Another thing, we start this is 1 year later, because that's also triggered by the conference. The very first conference, people complain that we have no place to publish that kind of research. And usually the journal don't like it at all. So we start our own. So you'll see that I have been the chief editor from the very beginning. And also we have a couple of people from Sweden. Okay. Patrick is in the board. And also some of you may know this name. Anyway, we do have something going on for more than 10 years, but it still is meant to be a very small community. But just in recent years, the phrase of AGI become popular. You know, many people are doing it, and many people are claiming they're doing it, and a lot of companies are talking about it, even though not many people really know what have happened in the last more than 10 years in this small community. So I think part of my responsibility is to explain to the outside what we have been doing and what make it different from the other AI research. Another thing is, even though we do have this small community of AGI researchers, we don't really agree on all the major topics. And later we will see gradually, except probably the only thing we agree is we kind of like are happy about where the mainstream AI is heading, and we want to go back to the big problem. That's about it. Other than that, later you will see that what exactly is the goal of the research, and what is the plan, what is the technique, and so we don't agree on any of those. So actually speaking, AI or AGI can be taken as as a research community or a small research field. But there is no such a thing as AGI theory or AGI technique, or in other words, there are many of them. Okay, you can even, in recent years, you can even say there are hundreds of them. So that's the reality. So it's still a very, in its very early stage, I would say. Okay, so that raises a challenge to me for giving this course here, right? So there is no way clearly for me to actually cover all the theory. I don't know of them, even though the one I know, we don't have the time for that. So instead of even trying that, what I'm going to do with the help of Robert and Patrick is to focus on our own research, for sure. But at the same time, I will try to relate to the other as much as possible. So whenever I explain one point, I will compare it with the other approach here or there. Especially today in the first lecture, I will try to give a larger picture. But after that, it will be more about our own research. But even though there are a lot of things in common, many of the problems are in common. So the first specific topic will be, of course, in any field, you need to specify your research objective or your goal, or in other words, what do you mean by intelligence or AGI? Okay. Beside what I just said, very intuitively, oh, yeah, treat intelligence as a whole, but still you need to say, what do you mean by intelligence? This is a well-known problem. I think anyone familiar with AI knows that within the field, there is no such a great definition of what intelligence is, not only in AI. The same problem happened in psychology to a less degree, but there's still, people have very different opinion about this. But at least one thing is certain, we all start from human intelligence. So some people say, in AI, the difference is whether you want to do it like a human or you want to do it according to some theory. I don't think that's a right distinction because everyone wants to do it like a human. The problem is what? The problem is in what sense? Okay. Human intelligence in this context clearly need to be generalized or abstracted to allow non-human things to be considered as well of them, like including computers. Okay. So now the problem is in this generalization or abstraction, in which direction you want to move and how far you want to move. That's where really the difference is. Okay. Another thing is, most people will agree, intelligence is a matter of degree. It's not just simply a yes, no, or whether you have it or you don't. Okay. So that will make things even more complicated. So later we are going to discuss each of the major or common perspective to generalize human intelligence so as to build a computer system in the same sense. But here, clearly we can see there are two extreme positions. Okay. Whatever you call it, it doesn't really matter. One extreme position is to define intelligence in such a way that it ends up only human qualifies. Everything else, just by definition, cannot be intelligent. That's clearly not good as far as AI or AGI is concerned. Okay. You're making your definition too narrow. You're not generalizing from human intelligence far enough. The other extreme, of course, you may have also heard about that kind of opinion, just basically say, since intelligence is a matter of degree, maybe we just should say everything is intelligent. It just, even this coffee machine is intelligent, it's just not much. That's another opinion. Both extreme opinion can be self-consistent, no problem, that's not a problem. Okay, of course you can have that, you can take that position. But both of them actually make this field or AI or AGI, whatever you call it. Impossible. Okay? We know we want to build this in a computer system which is not biological. So it cannot be exactly the same as human intelligence in all aspects. That's clearly out of the question. Okay. So if you say you have to be like human intelligence in all aspects, that just simply means this is impossible to do by definition. The other extreme, if everything is already intelligent, then this research is unnecessary to do. Okay, you can just build this function or that function. Why talk about intelligence, that big word? You don't need that. So especially here, there is something I guess many of you have heard about. It's called AI effect, as well as a couple of other names, but it's the same phenomena. That is, as soon as you achieve a goal, people don't think it as intelligent anymore. Okay? So you see here, the description is, it's kind of like you see a magic show. As soon as you understand how the trick is played, it's not magic anymore. So some people say, yeah, as soon as you have it done, people just say it's just computation. Or people just say it's just programming. Okay, what's the difference, right? Some people say, oh, AI means, to use a computer to solve some problem, and only the human mind can solve. And that will run into this trouble because how about arithmetic calculation? Before computer was invented, that's something only the human mind can do. Okay? If you count that as AI, then people will say, oh, that's a joke. Okay? That doesn't make much sense. So you'll see this kind of just use our intuitive opinion to guide the field is not enough, and also it does not give it a proper identity. Okay, and not to mention to try to establish a theory for this research. So where to start? My starting point is to think about, of course, you still need to respect the common usage of the language, right? Otherwise, you should use a different term. Why call it intelligence? What is the widely acknowledged form of intelligence? Not only in English, almost in all language or culture at the current time. Well, clearly, this is the best example. No one argue about that. And this is what we want to do. Call it artificial, you can call it computer. It doesn't really make much difference. Okay. And many people will argue animals, or some animals, are quite intelligent, even maybe less than human. But still, well, that's a accepted concept by most people. And also, very often we talk about a group as an individual. Typical example is we're talking about a company or a country as if it's a human. We talk about its intelligence, whether it's a stupid decision or what it thinks, what it believes, and so on. Okay, there's some truth. It's more than just a metaphor. So, and also finally, this is at least a logical possibility, right? Not just a sci-fi topic, and who can claim that human intelligence is the only possible form of intelligence in the whole universe? I don't think you can strongly claim that. You can just say, oh, I don't know any others. But at least there is a logical possibility. So now the question is, if we all acknowledge this, people think at least those phrases make sense. Then the next question is, what do they have in common to give them the shared title of intelligence? Well, here comes my working definition. This is probably the most important sentence in this whole lecture because everything else build on that. Okay. So I define intelligence as the ability for a system to adapt to its environment while operating with insufficient knowledge and resource. In different publications of mine, sometimes the wording is not exactly the same, but there's 2 points. One point is what we call the assumption of insufficient knowledge and resource, or AIKR, which I'm going to mention in every lecture in the following, because this is the foundation of the whole work. Intuitive meaning, very, very easy to understand. The system doesn't know everything, doesn't have all the time and space to try everything. Okay? Just that simple. To be more accurate, I define it with 3 keywords. One is finite. That is, the system only has finite processing capability. Like, for example, for computer, of course, we're mostly talking about computer. The number of processors, storage space, fixed. It can be huge. Okay, today's computer is already huge compared to, say, 30 years ago. And very super fast. It's still finite. And even if you use GPU or any fancy hardware, it's still finite. You may wonder, yeah, that's obvious. Okay, who said otherwise? Why do you want to mention this? The problem is, even though it sounds like a trivial reality, almost all the theoretical models ignore that fact. Okay, you want to store things, what if you don't have the space? People already say, oh, that's an implementation problem. Okay, in theory, for example, Turing machine. Okay, so later we will see that even though that's a clear, realistic restriction, to put it at your foundation of your theory, it will change a lot of things. Okay, so directly it means the system needs to manage its own resource. And another direct conclusion is, for example, our system will forget things. And later we will say more about that. Okay. At first, many people say that's ridiculous. Okay, what makes a computer better than human is it never forget. Well, to us, that's one reason why it's stupid. Because it doesn't manage its own memory, it depends on you. When the hard drive is full, you as a programmer or user, you need to decide what to delete. But a truly intelligent system should be able to handle it by itself. Okay. Second one is real time. And this is from computer science, well, everyone understand what I mean. It usually means there is a deadline, right? When we talk about the real time, we are using the word in an even stronger sense. We mean 2 things. One thing is a new task or problem, whatever you call it, may show up at any moment to the system. It doesn't come only when the system is idle, waiting for the next job. No, the system may be busy with something else, then there is something else, another task will show up. And you don't know when the next one will be here for you to deal with. So that's one sense. Another sense is, yes, there is, every problem has a time restriction or pressure associated with it. And deadline actually is only one special case. A more general situation is what we're all familiar with, that as soon as possible. I want a solution as soon as possible. Actually, you can think that's actually attached to all the problems we are dealing with, even though with different tolerance or different soon, what that soon actually means. Usually you cannot take whatever you want, how much time you want to spend on a task. So what does that mean? Later you will see that change everything in terms of, for example, computational complexity. Okay. What if I want an answer in 5 seconds, even though the answer doesn't have to be perfect? The algorithm that takes 10 minutes to finish will become completely useless. Is that very unusual? Is that requirement too much? Well, think about ourselves. And finally, open. Also, it sounds pretty simple. You just can accept the new information. But what we mean here is you need to accept all new information, of course, as far as you can recognize it, right? If it's a signal beyond your sensibility, then of course you cannot see it. Or if it's a foreign language, there is no way for you to take it. As far as the format or form is acceptable, you need to accept it with respect to the content. You should not put any restriction on what the content can be. Open to all news, good or bad. Open to all assignments, whether or not you think you can do it. That's basically what we mean by open. Okay. There are a whole bunch of direct implications. For example, the requirement or the input information may contain contradiction. Well, you heard from different people, they tell you different things. How do you handle that? And a task given to you, you guess you cannot do it. Can you just say, I cannot, or I don't know? So you see, all those kind of things, to me, that's what an intelligent system should be able to handle. Or actually, I put it into the definition, meaning, which is a very strong claim. If you cannot do it, you're not intelligent. Okay. So this clearly is a very controversial point of view. That's why I call it a working definition, right? What I mean? That means that's what I want to do in my work. And I know this is not shared by most of the people, but I do have a reason to believe that's closer to the heart of what we call intelligence, even though it may take some time for the community to recognize that. Okay. Another justification for this choice is if you think about human beings, we do work in this environment or under those restrictions, whatever you call them. But another direct consequence is, yeah, if you want to develop a system to work in that environment, what do you mean by work? If you don't really know everything with respect to the problem you want to solve, by definition, you cannot guarantee your answer is always correct. If you can guarantee that, that means you already know everything you need to know for that problem. Right? So, and also, if you don't have the time to think about all possibility, there is no way for you to guarantee the answer you provide is optimal, even among your knowledge scope. Okay? Because there may be something you actually know, but it didn't occur to you. You didn't have the time to think about the whole possibility. So if that's the case, how can we still claim such a system can be intelligent? Or in other words, in what sense the system, the answer is better than random choice? It's the second point. Adaptation. Okay. Adaptation in this context means the system, yeah, there's two aspects. Insufficient knowledge, which means that everything you know is about your past experience. You don't know the future. The future will not be exactly the same as the past. But adaptation means you are going to use the past or the knowledge you summarize from your past experience to handle the current and the future situation, even though you know it can be wrong or often wrong. Why? Because there is nothing else. You cannot depend on anything else. This sounds like a pure philosophical assumption, but later you will see this has direct technical implication. For example, next lecture, I'm going to talk about how to define truth value in our system. It's completely based on this position. Okay? You don't know the reality. So what? So when you say this is true, you're using your past experience as the reference point, not the objective world. You don't have access to that. And second part, you never have enough time. Then what? Then you have to live with it, okay? To live with whatever resource you have at the current moment and try to use it as efficient as possible according to your own judgment, which is summarized from your past experience, which can be wrong. But still, I can say, because of this analysis, we can still have an internal standard say that in what sense we say this is a better answer or more intelligent answer than the other one. Even though this standard is already fundamentally different from most of the traditional theory. Okay, so for example, in our system, we make prediction, we do not guarantee success, we do not even guarantee a success rate in terms of probability because we don't know the future. But it's not a random guess. It's justified according to what we do know from the past. So now I can go into a little bit of detail by justifying why I pick this working definition instead of the more common, popular one. Okay. First, compare this to brain modeling or so-called biologically inspired approach, which is quite popular, especially in recent years. Okay. The rationale is very justifiable. Again, I touched that before. Many people say, yeah, AI, we really don't know anything except one, that is human intelligence is the existing proof of intelligence which is produced by the human brain. Okay, so because of that, of course, the most reliable way to achieve artificial intelligence is to simulate the human brain as faithful as possible. That clearly makes sense. A concrete example, for example, you can see this recent book by Jeff Hawkins. This is a typical example of this approach. Okay, this is more than what they just usually call a neural network. That thing actually is not taken human brain that seriously. Okay, they're just get some inspiration. And this approach is much closer. They really want to duplicate the brain as faithful as possible. Why I don't want to do it that way? Well, the common objection or criticism to this approach is approach to do AI. First, of course, it's very difficult. There are a lot of things that we don't know at all about the human brain. Okay, there's still a lot of mystery. But that's actually not my major reason, because difficulty, in scientific research, you cannot say, I don't want to do this just because it's hard, right? That's not a good reason. To me, the major reason I do not follow that approach is the other two. It's whether it's really necessary and whether it's general enough. Okay. And first part is the brain and the mind. And they're clearly, these are two different concepts. They're related to each other, yes, as I mentioned previously. The human mind is produced by the human brain. Well, yeah, sense we can say that. But that doesn't really mean all possible minds must be produced from a brain-like structure. A metaphor which has been used hundreds, if not thousands of times in the field, I think everyone is familiar with, is flying and flying like a bird. That's two different topics or two different tasks. Also valuable, okay? But it doesn't mean flying means you have to fly like a bird as much as possible. Or you can learn from birds, that's for sure. So that's my major reason. I have high respect to the colleagues who are studying how the brain works. But to me, it's a separate topic. Okay? It's related to artificial intelligence in the general intelligence sense, but it's probably not the best way, at least that's not the way I want to pursue. Also because this is kind of like too close to human intelligence, as I mentioned before. Okay, it kind of like, yeah, we want to learn from the brain, but we don't want to use to let that to limit our ability of imagination. Is there any other way to do the same thing? And of course, it depends on what that same thing means, right? So in my working definition, I already make it very clear what I want to do. I want to build a system which can adapt your environment, or you can say what we call insufficient knowledge resource can be summarized into another one single word, that is a realistic environment. Yeah, realistic environment, you have finite resource, but the demand is always beyond that. And you have to open to new information. I want to build a system to work in that kind of environment. Okay, whether the structure is like the human brain, we will see. Okay, maybe later we find it have to be similar to brain. Otherwise, you cannot work at all. Well, then I will accept that, but I'm not going to set that as my goal at the very beginning. So, or in other words, I take brain as a source of inspiration. I learned a lot from the human brain, just like many other people. But I do not take it as a source of justification. Later you will see, when I talk about one design decision in our system, sometimes I will say, you see, this is kind of like similar to what our brain does. But I'm not going to say I make that decision simply because it's similar to what the brain does. That's not enough. They give you some clue. Okay? And especially, I'm strongly against the idea of to be as faithful to the brain as possible. Because in human brain functionality, and mechanism, there are a lot of things which actually mostly come from the biological nature and also from the evolutionary history, which I don't take as absolutely necessary for all types of intelligence. Okay, that I believe is an intuition shared by many AI researchers. I just make it very clear that's the case for me. So the second group, and this is a group of people actually share my opinion I just said against brain modeling. This is a group of people say that whatever the structure is within the system, that's a secondary. What really matters is external behavior. Okay, so if you can produce something which in the external behavior, it will be just like human. Who cares what is inside, whether it's a brain-like structure or not? Well, everyone knows what I'm talking about. Okay, this is the idea behind the Turing test. Okay. So if it's linguistic behavior cannot be distinguished from a human being under certain condition, you have to say it's intelligent. That's Turing's argument. So what's our challenge? First, of course, it's very difficult. And even though in recent years, there are many people claim they have passed the Turing test in a certain sense. But to me, again, that's not the major reason I don't like it. It's the other tool, which is kind of similar to what I said about the brain model. Is that really necessary? There is a common misunderstanding about Turing's paper. I assume here most of you have read about it, okay? But there is a paragraph which is even very, very rarely mentioned in people's discussion. I cannot remember the exact word, but I can find it for you if anyone wants me. Turing made it very clear. His definition or his test is proposed as a sufficient condition for intelligence, not a necessary condition. He didn't use those two words, but basically, he said, if some computer pass that test, you have to say it's intelligent. But there is a possibility that that computer failed this test or cannot pass the test, but it can still be considered as intelligent for other reasons. He acknowledged that possibility. He just said that since I think the test can be passed in the near future, in his prediction is about 50 years, right? He said we don't need to worry about that objection. But he acknowledged that. So clearly he's not suggesting to behave exactly like a human as a necessary condition for something to be intelligent. Think about it. That's way too human-centric point of view, okay? We think about ourselves. Well, that's why, actually, a reason why I mentioned alien intelligence as a possibility, okay? And you check whether an alien is intelligent or not using a Turing test. That sounds like a joke. Well, clearly it is a joke. Okay? But if that alien intelligence is so smart that it learns everything about human, then it can successfully pretend to be a human. Of course, we will say it's intelligent. So in my opinion, Turing test is still a sufficient condition for being intelligent or being able to think whatever word you use. But it's not a necessary condition. Especially, it makes the circle too narrow, too close to human intelligence. Okay? So yeah, why should AI pretend to be a human to be considered as intelligent? Why not the other way around? Okay? So eventually, given my definition, actually I have a strong reason to against pass a Turing test. That is, I think intelligence is a form of adaptation. Adaptive means what? I mentioned to behave according to its own experience, to learn from its own experience. And AI's experience, we have all kinds of reason to believe will not be the same as human intelligence, as human experience, because they clearly will have a different body. And body matters, they have different sensors, they get different information, and they have different motivations. They don't have biological restriction motivation at all. But they can pretend to have, that's a different story. And some people say they can simulate, that's also a secondary issue. Okay? And you cannot, even if that's possible, to say that only when they can do that, then we will acknowledge them to be intelligent. That doesn't sound fair. Okay. So I made it very clear that my own research is not passing the human Turing test as the goal. Not because it's difficult, because I don't think it's the right direction. Even though maybe it become, one day so smart, and just for fun, okay, pretend to be a human. It's possible, it's still possible. But I don't want to design a system. Just take that, that's what they want to do eventually. So eventually, if we want to be concrete, think in the context of robot. Today's concrete robot. And some of them have sensors and actuators which are completely different from human beings. Do you expect them to pass a Turing test, or you will say, just because of your body, there's no way for you to be intelligent? That's ridiculous. Okay? But we still see this in today's newspaper and even some academic publication that take the Turing test as the definition of AI, which even Turing himself will not agree with that. So that also means another practical thing, later we'll see in my own work, even though I have been trained as a computer scientist, my work has been very, very strongly influenced by psychology. Okay, I learned much more from psychology than from neuroscience, as you can guess. Okay, as a level of abstraction, I think psychology is much closer to what I want to do. But there is one thing I keep reminding myself whenever I'm reading any conclusion in psychological book, is that whether that conclusion is only about human intelligence or it also applies to all forms of intelligence.
Could you maybe give a concrete example of something that you learned from psychology that is better than what you learned from neuroscience, I guess?
For example, a model of concept. And later we will quite spend some time on that. In psychology, there is a huge literature on different model of concept, let's say prototype and theory, and so on. I don't agree with all of them, but I learn from each of them to a certain degree. If you see neuroscience, they typically do this experiment and say, oh, when you see this experiment, there's some neurons activated, blah, 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 blah. Yeah, that's true, but so what?
Yeah.
So yeah, we will say more about that. So you will see there is a very close relationship between my work and psychology, especially cognitive psychology, and I also my PhD is a joint degree in computer science and cognitive science. So I do learn about especially cognitive psychology. But there is this distance I deliberately keep from their conclusion and try to identify the functional necessary thing from the biological or evolutionary accidents, which well, you can still do it. It just is probably not really necessary, and that will narrow down the possibility scope of your design. Now, this is more from a practical point of view. AI people typically ask me, whenever I talk about my research, typically ask me, oh, what kind of practical problem your system can solve? That's a common question in the field, right? You need to be able to solve something to claim to be intelligent. But it's a tough question for me because, frankly, I should say none of them. Because my system is not designed with respect to solving any concrete problem, which may sound weird, because they do have a reason to say that. Because when we say, for example, we judge people's intelligence, that's where the concept of intelligence comes from in psychology, right? they have to evaluate people's different intellectual capability. And so they start this kind of research and IQ test and so on. So we do evaluate other people's intelligence according to what type of problem they have. Because we cannot really open their mind or study the mechanism there or whatever more abstract way. Okay? So this is the practical standard. Example is all kinds of expert system. Well, now some people does not use that phrase, but it's still specialized system which can solve one problem very well, but nothing else. All those kind of systems, like including the recently famous, say, AlphaGo, okay, and the attempt to drive a car by a computer system and all those kind of things. That's of course very valuable. What's the problem? From my point of view, at least I can mention three. The first one, actually, this is directly responsible for what I showed before as the so-called AI effect. Okay? So if your target of your AI research is to solve one practical problem, most people will do what? They'll do it in the traditional way, which end up where you solve the problem and you build your solution into the computer. Then the computer will just repeat your solution. That's why people have the feeling that as soon as the problem you have solved is solved by you, and we don't see any intelligence in your computer. And another thing is, yeah, I think I have touched that. Which problem? As soon as you decide a group of problems as the standard of intelligence, then you run into this AI effect. As soon as they are solved, they're done. Okay, you need to pick another group of problems, say, okay, then what? The AI become a moving target. That's probably not really an issue in industry, okay? But it's a problem for people who really want to build a theory for intelligence. Because you cannot build a theory for a moving target. Okay, each time the target is different, your solution is different. And what are there anything in common? Well, they use computer. Then they go back to what? To computer programming, to a theory of computation, and so on. Okay? So it become, so-called AI become a new label. You put on your solution, which actually is built according to old theory. You don't really need this label, except for commercial, purpose to make it sound better. For example, in recent years, a lot of things which we traditionally called computer application or automation, now are all called AI. Okay? Can you have a theory for all of them? So you don't give this domain a correct identity for you to really develop a theory or to really study anything which is not superficial. Another thing is, even if you have solved that problem according to the traditional theory or approach or technology, you see that many people still have this gut feeling, which I had from the very beginning. That is, what we know today's computer already can solve a lot of problems much better than us. It's very easy to get a long list of them. Actually, the other way around. Everything today's normal computer can do, we cannot do better. You cannot search the web better. You cannot edit a file better, right? But we don't call them intelligent. Actually, we have the feeling that even though it's done, there is something missing. Like, for example, originality, flexibility, those kind of features are actually what bring many people to the field of AI in the first place. They think the traditional computer is very powerful, can solve a lot of problems better than us, but there's still something missing. For example, I said, it basically is still run a program designed by the designer, just using its computational power, use its speed and the storage space and the information source and so on to beat us on that task. Okay. That's good. But the missing part is who solved the problem? What if, you go back to my working definition, what if I give such a system a problem which is not anticipated by the system itself or its designer? What can I do? Nothing. Okay, if I ask my laptop to do something, there is no program already designed for that task. It will not do it, and guess what? It's not its fault, it's my fault. Okay, none of us should ask this computer to do that because we know its capability. We know it cannot handle that situation. We know it's not original. We know it's not flexible. By changing its strategy according to the context and so on. But on the other hand, we do expect a truly intelligent system to be able to do that.
I'm a little bit confused. So this is not about whether they can solve the problem, but rather whether there is a possibility to learn to figure out this.
You can put it that way. So in my definition, it's not a problem. What the problem it can solve is the condition under which it can solve it. That's what matters. Okay, later I will explain more. Okay, learning clearly is a key factor. Even though I don't use that in my definition, I use adaptation, but basically it's the same thing. I avoid that word exactly because machine learning research, they have already given it a very special meaning, which I don't agree, which I will explain later. Okay, my system clearly is a learning system, but it is not a machine learning according to the current definition. So yeah, let's touch that. That means adaptation or adaptive system means to be able to change its behavior in its problem-solving process, okay? Rather than either follow a predetermined algorithm or form a predetermined or learn algorithm, then follow it. In either case, that's not what I mean by adaptive. So you can say, okay, actually is what matters is not what it can do, is what it can learn to do. And that's another way to put it. Clearly, these two are at different level. Actually, our system, later we'll see, after we build it, is more like a baby. There is no built-in problem-solving capability, and you need to teach it. To me, that's what intelligence is about. But of course, from a user's point of view, okay, people are not happy about it. They say, we want your system to be able to solve some problem. We think that's what intelligence is about. And we can talk about how to handle that situation later. But that's the difference. So you'll see, basically what we're doing is more a theoretical model with application potential. So that's the argument I have with the potential user. I say, oh, yeah, currently it's just a baby. But if you train it right, it can be very smart. Okay, so that kind of story. I will have more material to support this claim later. So another more standard official definition of AI is to define AI as a collection of cognitive functions like reasoning, learning, planning, problem solving, perceiving, acting, communicating, and so on. If you pick any AI textbook, you check the title of the chapters, that's it, okay? That's actually the practical working definition of AI, accepted by the community over the years. So if you do anything related to one of them, you can submit to an AI conference, and the editor cannot say it's irrelevant because I'm doing learning, I'm doing reasoning, and so on, and they're included under AI. And this is taken to be common sense in the field, okay? Actually, I agree with this opinion more than the others I just mentioned, but I still am not completely happy with this definition for two reasons I mentioned here. One is, well, again, you get a whole bunch of things putting together. You use this intelligence just as a suitcase word or umbrella, which cover a whole bunch of very different stuff. What makes them? What's the common feature that make them into this set? You still need to have some standard to say, oh, what is needed, what is not. Okay, people now intuitively just say, oh, this is also what we can find in the human mind. As I said, we can also find the function of doing arithmetic calculation in human mind. Why don't you count that as AI topic? That's one thing. Another thing later we'll see is more related to engineering consideration. So if you really want to build AI as a whole, this idea will intuitively guide you to build a mixture of functions into one system, which later I will argue is not a good idea. Okay? Or in other words, if you check the current AI textbook, and some of you may be actually teaching an AI course, if you have ever done that, you know what I'm talking about. It's more like a sequence of lectures rather than a coherent theory. Because, for example, the current theory of learning and the current theory of reasoning studied in AI are built on very different theoretical foundations. Of course, you can implement both in the same computer system, but it doesn't mean they will work together properly. Okay. Later, we will say more on that topic. So that leads to another thing that some people mentioned, half as a joke, half serious. They raise the concept of AI completeness, kind of like it's an analogy NP completeness. That's where the idea comes from. What they basically want to say is, well, yeah, you can list all the functionalities separately, but until you solve all of them, you cannot solve one of them completely. Okay, for example, yeah, natural language processing is one domain. Learning, reasoning, and robotics are the others. But can you really understand natural language without solving the problem of perception, reasoning, and learning? Well, you probably can do 80%. That's what the deep learning recently tells us. Right? They can do pretty well in machine translation without understanding what this is talking about. But the remaining 20% or 10% or whatever it is, there is no way for it to do. Because it needs other cognitive functionalities. So this is a picture which intuitively shows this idea. Some of you may know where this comes from. What is this? Is this a letter D, a letter B, or a letter E? All three. It's all of them all together. The most important thing is it's not a D and a E and a B combined. Okay? So that leads to my argument. Here, we have separate phenomena observed, especially from human intelligence. But that separate phenomena does not justify their separate mechanism underneath each of them, independent of the others. Okay. Actually, I'm taking a very extreme position, like that photo shows. In our system, later I will show you, there is only one process, okay, which shows all this kind of phenomena. To be more specific, reasoning and learning, that's the two major cognitive functionality. And the traditional way to handle it is to have a separate learning algorithm and the reasoning mechanism, then connect them to each other. And in our model, reasoning and learning is the same process. But you can still see these two different phenomena when you observe it from different angles, just like in that photo. Okay. Of course, I need more technical detail to support this claim, but I want to make it first, okay, just to show you why we claim our approach is fundamentally different from most of the other approaches you have heard about. So the idea is, instead of trying to solve this and this and this and this, is to find a common root, which is what I call adaptation with insufficient knowledge resource, and try to use that as a single foundation to develop technique which eventually solve everything or almost everything. Okay. This idea by itself also is not really new. And we know if we think about science, or if we think we're really doing a science of intelligence, that's the most natural idea. Because every science starts from several basic principles. Okay, they use it to explain a huge number of different phenomena. They don't try to introduce a different mechanism for each of the phenomena they want to explain. So this is a very natural idea. And also some people have tried. Okay, we see this kind of conclusion from other people's work. For example, they think intelligence is ability to be always to be able to do the right thing. And that actually fits our intuition. When we say someone is intelligent, he or she always be able to make the right decision. Of course, that shows intelligence. So we have all kinds of classical models of rationality. And in AI history, the first few decades are dominated by classical logic. Okay, logic study what? Laws of thought. If you want to build a thinking machine, of course, it's pretty natural. We summarize the human logic, and we make a computer that follow the same logic. And that is the thinking machine. But we know it doesn't work well. It basically failed. And even though there's some concrete success here or there, but the big picture doesn't work. Then now is what in recent decades. The dominating model of rationality is probability theory, okay, including almost all machine learning and many other fields. Okay. The techniques and results are justified according to probability theory. And why? Because it's correct, right? It's a model, and or rational people should behave according to probability theory. Otherwise, you're making mistakes. Again, next lecture, we are going to go into detail on that topic. Okay. But what's the challenge? Why I don't agree with them? I agree that we should find a basic principle and build everything on top of them. My question or my problem with their choice is they're way too idealized, okay? Traditional logic is way too clean. Everything is either true or false. It's not that simple. The reality is much more complicated than that. Probability model is moving in the right direction compared to binary logic, but still not far enough. Okay. They acknowledge the uncertainty about the occurrence of the event. You say, oh, I don't know whether it will be head or tail when you are tossing a coin. It's a probability thing. But what? But they assume they know the probability, or they assume that there is a true probability to be discovered. In my model, we don't even assume that. Then what you should do? Okay. So again, I will argue this is not just a theoretical issue or philosophical, people have different beliefs. It's more than that. It's directly about the applicability of that model. Why many traditional models don't work well? Their assumption cannot meet the reality. Their assumption is way too simplified or too idealized. For example, you assume you know everything. Okay? Many, say, expert systems assume what they know, even though it's not everything, but it's the correct things. Then they will run into trouble wherever one of their assumption is a challenge by a new case. They cannot handle that. And probability theory, more complicated, but it's the same in the same direction. For example, they assume they have a consistent probability assignment among all the events. Do you always have that? So I would rather build my theory on a more realistic assumption about what the system knows, what the system can do. Even though that means you need to pay the price. It's not free. There is nothing magical. We pay the price. I already mentioned, I gave up the idea of always guarantee the success or optimum of the solution. We cannot do that. And as a result, you'll see, that's why today I spend almost all the time to talk about philosophy. Why? It is because all the following technical decisions are based on today's lecture. And you will see that. So what I'm suggesting later we'll see is a form of relative rationality. That is, I still want my system to do the right thing, but that what is right is with respect to what the system knows and how much resources the system has at the moment. And that change. And finally, how to do it, how to build such a system. That's, of course, that's something we are going to use the next 7 lectures to answer more. But today I will give you, again, the big picture, especially compared with the other approach. With respect to AGI, in my opinion, the current approach very roughly belongs to 3 major categories or 3 groups. The first one is what I call hybrid. And in recent years, there are several papers argue the next generation of AI should be hybrid. Well, it's understandable. Everyone sees the great success of deep learning. And also, at the same time, more and more people see its limitation. It doesn't do everything well enough. Again, my previous example, learning and reasoning. Okay, it do learning reasonably well, but reasoning, there are all kinds of trouble. Why not use a reasoning technique together with the learning capability provided by deep learning? Like either use traditional, some people talk about the PSYCH project. Okay. Some people talk about the Bayesian network as a reasoning model and hook it up with deep learning, why not? So what's the problem? Of course, there are some reasons. We also, our team also do that kind of thing, okay? whenever we do a special application. That means if you want to do a special purpose system, but use some AGI result, probably most practical way is to do a hybrid system. By using the existing AI technology as much as possible as your parts. But this is not the way to do AGI. Not only I have this opinion, actually most people in the AGI community share this opinion. Otherwise, we will stay within the AI community and work with the others in this building block way. Okay, you're doing reasoning, you're doing robotics, you're doing vision, you're doing natural language. Why not we work together? You know, we do everything all together. It sounds very good, but as soon as you begin to try it, you know it's not going to work at all because of the issue I mentioned. All those technologies are built on very different theoretical foundation. They're not compatible in general. For a special problem, you can twist them to make them work together. Okay, but not a general solution. So the AGI people usually take the middle approach. That is, even if you want to use multiple technology, you need to have a blueprint first about the big picture, which is typically called a cognitive architecture or some kind of architecture. Okay, then you begin to build the parts according to the role they played in this architecture. So still talking about reasoning and learning, okay, in this picture, you need to first, instead of talking about this two technique, you need to talk about their interface. What problem will go to which side, what's the format of the information they exchange, and how to control if they have different opinion or there's some other conflicts. Finally, this is the approach we are taking. Again, it's a very extreme position, which is what we call a unified. The idea is use one single technique. But of course, from an engineering point of view, you still have to do it step by step. Okay, so what we are going to do is we start with the foundation, which is relatively simple. Then we build another layer on top of that, then another top of that. Again, using the concrete example of learning and reasoning. You see, in this picture, this will be a reasoning model, and this will be a learning model. Each of them can be used by itself. In this picture, let's say this is the learning part, this is the reasoning part. They cannot be used by itself because they depend on each other. But you can still clearly separate them within a system in terms of the functions. In our model, even at the basic level, learning and reasoning happen together, but in very simple form. Then in the second layer, we do more complicated reasoning and learning. And in the third layer, we do even more complicated. So it's still step by step. But the steps are not cut in this way. Okay. Again, I will explain the details later. So that's basically it. So what I have here is a list of AGI, representative AGI projects, which I maintained in a web page. And this one also, I referred last slide, the selected readings for today's lecture is this one, so you can have it later. Okay, this is a page I maintained for more than 10 years, just because I keep getting questions about this AGI. So a lot of stuff I have in this page I already covered, but what I'm talking about is here. I have a list of what I consider to be representative AGI projects, which are not the one that I agree with. Actually, I disagree with most of them, okay? But I picked them according to 3 standards. First one is clearly AGI oriented. You're not allowed to say, okay, what I'm going to do is something which is part of AGI or is a step toward AGI without talking about the other parts, okay? So you need to show us your overall roadmap, even though you're only halfway. Second one is still very active. I have, as I said, I have some project which was in early version of this page, but I later delete them simply because I'm pretty sure that that project will not continue, either because of the leader passed away or turned to something else. So I removed them. So all the ones I have here are active. And finally, they need to have enough material. Okay, especially in recent years, you heard about this over the internet. Every month, some people say, yo, I already solved this AGI problem. I'm not going to tell you, that's my commercial secret. Or you need to give me, funding, I will tell you. I cannot say they're lying, okay, because I don't know the detail, right? So what I'm listed here are the ones that gave you enough material to analyze and criticize. Okay, so just one paper, even though that paper I like, will not make that project into this list. So I have now about a dozen of them that satisfy the condition, which for each of them, I provide 3 links. One go to the project website. The second one go to a public downloadable short description about the project. And the third one is a more comprehensive description. It typically takes the form of a book. Usually, you cannot download it, even though some of them you can. And then I pick a few paragraphs from their own website, which summarize their answer to the 2 questions I addressed today. First, what's their goal? To be accurate. Okay? In what sense they say their system is similar to the human mind. Second one is how they plan to do it. So then I summarize them into this 2-dimensional matrix, which is also here. According to what they want to do, or in what sense is similar to the mind, and how they plan to do it. Okay. So that's what this is about. If you're interested, you can take a look. I'm already running out of time. And finally, at the end of each lecture, I'm going to give you some suggested reading. It's really suggested. Okay. And part of them from other people's work, part of them from my own work. And for my own work, you already have this link, right, which gave you access to the material we use for this course, which are the 2 drafts of my previous publications, which is what I'm referring to, okay, at the end. So that's all for today. Sorry for being out of time for 10 minutes, but I think we can combine the discussion with the break, wherever.
So let's have 10 minutes of stretching our legs and using the intelligent coffee machine. And then we will take questions both from the audience and from Zoom. But some